Steve. And here we'll talk about the disorder ultra-cold gases. Yes, welcome.
Thanks. All right, let me get the mic set up. Okay, so I am an ultra-cold atom experimentalist, and I've been for a long time working on measuring and trying to understand thermalization in ultra-cold gases and also in disordered ultra-cold gases. So I have 3 lectures I'm going to give, 2 today and 1 tomorrow, and these are the topics. The first one will be just on ultra-cold gases, so nothing to do with disorder, but just background material which will be woven out throughout the next 2 lectures about ultra-cold gases and how they work and how you should think about them. The second lecture today, at the end of the day, will be about how do we make disorder and what does it look like and how should you think about it in these experiments. And then the third lecture will be kind of an agnostic lecture, a survey of all the types of localization-related phenomena that have been observed in these experiments. And I'm not really going to go into what is MBL, what is not MBL, just a survey. So most of these lectures are kind of in that spirit. They're a survey to get you started. So give you basic information and then point you in the right direction if you want to find out something else, okay? Because it's sort of impossible to give you everything you need to know in 3 lectures. The other thing, let me say from the outset, is that it's kind of hard, it was a little hard for me to gauge what you might know and what you don't know, especially because I am an ultra-cold experimental physicist, and I'm kind of coming from a different area. So please interrupt with questions. We can diverge into different topics. I have lots of backup slides. If something's boring, you all know it. We can skip that. There's plenty of material here. And so I hope I get lots of great questions, just like you had questions for David. So please just interrupt me. And I think that's it. All right, so why don't we go ahead. So the first topic, hopefully this isn't too boring, but it's really just going to be what are ultra-cold gases like and how should you think about them? What are some of the basic physics that you need to understand the second 2 talks? Okay, so this is all about ultra-cold gases. So we make ultra-cold gases with atoms, we use atoms. I'm going to talk about today and tomorrow just experiments with neutral atoms. There's also experiments with ions, but that's kind of a whole different world. And by this point now, it's 2016, people have trapped and cooled many, many different kinds of atoms. Actually, far more bosons than fermions. And for the most part, people still use alkali atoms. So rubidium, sodium, lithium, cesium, potassium, and that's about it. And so the examples I use are really pertain to alkali atoms, but you change things a little bit and it'll work for the alkaline earths or the lanthanides, which are recently cooled atoms and things like that. All right, so we work with atoms, they're neutral atoms. And when I talk about these atoms being bosons or fermions, I'm really talking about what is their total spin, the hyperfine spin, which is the spin you get from the nuclear spin I and the electronic spin J. All right, so remember, the alkali atoms, which are going to be my example, they have 1 valence electron. We're going to be talking about the spin of that electron combined with the spin of the nucleus. And so examples, for example, would be rubidium-87. Its nuclear spin is 3/2. And so it has, when you combine that with the ground state electron spin, you get hyperfine states of total spin 1 and 2. And so it's a boson since that's an integer. And we talk about potassium-40, one of the few fermionic atoms we have. Its nuclear spin is 4, so you combine that with a half and you get 9/2 and 7/2. So it's a fermion. So bosons, fermions, we're just talking about the total hyperfine spin. Okay, so let me give you an example then of the states we use of the atoms in these experiments. So we always work with the electron, now alkali atoms, so that 1 valence electron, and its ground electronic state, so an S state. And we, in the types of experiments we do, we control and we resolve all the hyperfine states. So example, for potassium-40, we've got, oops, and I didn't label all these, but potassium-40, the ground state electron's in a 4s state. There are 2 hyperfine ground states, F equals 7/2, and this one's F equals 9/2, so I lost a label there. And there's a bunch of Zeeman levels. In these experiments, we resolve and control all these states. So for example, let me also just say, 1 energy scale here, which is relevant, is that hyperfine splitting. For potassium-40, that's about 1 gigahertz, and that comes from the interaction of the electron with the nucleus. Okay, so for example, in these experiments, we may pick out two of these Zeeman states, hyperfine states, and have the atoms only in those states. So for example, in the experiments with potassium-40, we often choose the MF equals 9 halves and MF equals 7 halves state and the F equals 9 halves ground state. Now for single atoms, those states, you should think about them as being stable in the lifetime of the universe. And they really are. So if we put atoms, if we put 100,000 atoms in MF equals 9 halves and 100,000 atoms in MF equals 7 halves, they stay 100,000 and 100,000 basically forever within any experiment we'd ever do. So the individual number in these states is conserved for most experiments. There's also a Zeeman energy I've put in here, right? All these Zeeman states are split. We also typically apply uniform magnetic field in our experiments. And so there's some Zeeman splitting, which may be much smaller than hyperfine splitting, maybe a few megahertz in typical experiments we do. All right, so those are the states we pick out for the experiments we do. All right, so what do we do with these atoms? And let's see if this works. It's probably not going to be super visible anymore. All right, so we so we trap and cool these atoms in a vacuum system, and that vacuum system is like our thermos. It's our insulation from room temperature and thermalization. And cooling and trapping progresses in a series of stages. So it's in a vacuum system. Typical vacuum system might be a meter cubed, something like that. And we introduce the atoms as a weak vapor into this vacuum system. And here's a glass cell from one of my experiments. And the first stage of trapping and cooling is using laser beams where we shine light at the atoms. And I don't know if this will work or show up particularly well here. I don't know if you can see that, but we have a vapor of atoms in there. We shine laser beams at them from every direction, and we apply a weak magnetic field gradient. And the atoms scatter that light, and they're trapped and cooled. Then we might start with about 1 billion atoms there, cooled to about 10 microkelvin in that magneto-optic trap. So that's the first stage of cooling. Okay. Of course, these atomic gases are always metastable because even at room temperature, they're a solid. So we work with them in a vapor. We make the density low enough so that process of solid formation is suppressed and occurs at a long enough time scale that we don't have to worry about it. So then typically, there's a second stage of cooling called evaporative cooling, where we trap those atoms, let's say, with magnetic fields and or light. And I'll talk a little bit about how that works. And we trap them in a trap with a finite potential depth. You can kind of see that here. Those atoms collide with each other. And as far as we understand it, and David raised a lot of great questions, we'll come back to them several times, those atoms collide and thermalize with themselves. Now, one thing you'll see here is that potential depth, we're lowering in this experiment. So successively lower energy atoms escape from this trap. The remaining atoms collide and thermalize and reach lower and lower temperatures. Typically, we cool down in this stage to about 100 nanokelvin or a nanokelvin. We've thrown away almost all the atoms, but we may have about 100,000 atoms left. And this is really our starting point for experiments now. And that neutral atom gas that's trapped that we'll work with. Then we do something. Yeah, go ahead.
So this is a question that actually came up a little bit during the last one. How do you measure temperature?
I will come back to that, how we measure temperature. Okay. So what we have to do in these, it's a great question. And we only know how to do it in some very specific cases, because we have to use a property of the atoms to measure the temperature. Right? There's nothing in there. There's not a thermocouple.
Not a very small thermometer?
No. So we have to use a property of the atoms to measure the temperature. That means we can only really do it in cases where we understand the physics. And a big unsolved problem in this field is how do you measure temperature and say when we make these atoms strongly correlated, we don't know the solution to Schrodinger's equation. How do you measure temperature? That's a big, serious problem, actually, which is basically unsolved. A graduate student of mine wrote a review paper about this on Reports in Progress in Physics, and that's one place you can look if you want to know more about the big picture. Yeah. So I'll talk more about how we do it for a weakly interacting gas, which is kind of what I'm talking about here.
Interesting.
Yeah. Okay, so all of our, and actually that segues into the final thing here. So we do something to the gas, we manipulate it, we shine laser beams, more laser beams at it. Our experiments always have lots of laser beams. All right, we do something, and to measure what happens, we take an image. That image is taken by shining light on the atoms. The atoms, it's resonant with the electronic transition in the atoms. The atoms scatter that light, produce a shadow in the laser beam, and we image that shadow onto a CCD camera, and then invert it to form some kind of density profile. If we take a picture of the atoms while they're in the trap, that's their density profile. In, I would say still most experiments, what we do is we turn off that trap, we let the atoms release, they expand, and they expand for some amount of time, maybe 20 milliseconds or so. So the highest energy atoms, or highest momentum atoms, expand very far, the lowest momentum atoms don't go very far at all, and that will then provide us a momentum distribution when we image it. And actually for cases that are simple, from that momentum distribution we can infer temperature, and I'll talk about that. Okay, so that's how a typical experiment works. That whole cycle might take, somewhere between 20 and 90 seconds to produce an ultra-cold gas, do something to it, and then measure its properties. Okay? Yes?
Excuse me, how do you determine the number of atoms in the trap?
Great question. So how do you determine the number of atoms? Thank you for asking these questions. This is fantastic. So we can determine the number of atoms from the total absorption. Okay? So one of the great things about atoms is, for example, for alkali atoms, we know their properties incredibly well by this point in time, because people have been working on understanding atoms for over 100 years. So we know how much light one atom will absorb incredibly well. So by measuring the total absorption, we know how many atoms there are. That's one thing we can measure actually unambiguously in the experiment. That doesn't take any theory. Any other questions?
And so absorption doesn't change. Say if there is some base condition, it still stays the same as number of atoms types.
Yeah, so so to be very specific, atoms, when you shine light on them resonantly, they absorb with an absorption cross-section, very simple cross-section. And that cross-section is very close to the wavelength of the transition square.
So many-body physics doesn't change anything here.
No, so me and other people have proposed over the years trying to see changes in light scattering from many-body physics, but this is a very subtle effect. Okay, and that more does things like, it can change the overall absorption cross-section, it can change the angular distribution of the scattered light, but these are very, very tiny effects that no one's really managed to see particularly well yet. So that, to be specific, that absorption cross-section is 3 lambda squared over 2 pi. Yeah.
Sorry. So do you measure the number of atoms for only processes for which, each atom emits light, it's proportional to n? Or how do you try to know that you are not in a situation where they're doing something like synchronization or something? Like, how do you separate these situations?
Yeah, so there are things like superradiance, for example, where the atoms are close. They may absorb or emit light in different ways. But we sort of understand and know all that physics really well. So if that ever happens, we can take that into account because we know what's going on. For most experiments that happen here that I'll be talking about, these things are largely irrelevant. Okay, but that physics like superradiance is really well known and understood. This is what atomic physicists, really I'm an atomic physicist. That's what we've been working on for quite a long time. So we understand, what I'll come around to in this talk is that, the properties of atoms, these are things we know and understand very well. And that's what makes these experiments kind of interesting, because in microscopic physics, the Hamiltonian, what 1 or 2 atoms are doing, or 3 atoms, we understand incredibly well. So it lets us separate out the sort of microscopic physics from the many-body physics, which is maybe, in my opinion, the more interesting part. Yeah? Sorry? Oh, yes, this measurement is destructive. Okay, so we make one sample. This measurement is destructive. It blows the atoms away, and then we start over again. So it's not like an experiment on solids where you put a sample in a cryostat and you measure. We take maybe 30 seconds to make a gas. We do something to it. We take an image like this. It destroys it. We start over. So in these experiments, what makes them a little bit hard is they involve a lot of components. They're designed to be extremely reproducible. This is what makes these experiments challenging, actually. So that when something changes, we know it's because of something we did on purpose, not because the building shook, or a truck drove by, or, cosmic ray came through. Okay, that one's kind of hard to deal with. Okay. Great. Thank you for asking so many questions. Like I said, there's stuff in here I can skip to get to the good meat. Okay, so let me just orient you with some characteristic scales of these experiments. Since this may be not familiar to a lot of you, what do these gases look like in a little bit more detail here? Well, all the things I'll talk about today, the atoms are in a harmonic trap, a parabolic trap, so you know what the energy spectrum of that looks like for a single particle. And that trap frequency may be, let's say, 40 hertz. So the energy level spacing is h bar times 2 pi times 40 hertz. If I have 100,000 atoms, which might be a typical number of atoms, that means something like the Fermi temperature is about 160 nanokelvin. Okay, so these things are really cold, but there's not many atoms, by the standards of stuff we have around us. And of course, another important time scale here is, say, the trap period, which might be 10, 20, 30 milliseconds, something like that. That's a characteristic time scale in these experiments. Another characteristic timescale, if we trap these atoms in an optical lattice, which I'll only touch on briefly. In fact, I'm not going to talk a lot about my research in these talks. It's mostly going to be pedagogical. If we also superimpose an optical lattice, which I'll get to, a tunneling time might be 1 to 10 milliseconds. So that's another characteristic timescale. The size of these things in this trap, and you see stuff's cut off at the bottom a little bit, I'll keep that in mind, might be about 20 microns or so. Okay? That might be the size of that trapped gas.
What is the time?
So in a lot of experiments my group and other groups do, we might superimpose a periodic potential called an optical lattice. And so there's some tunneling time for an atom to tunnel from site to site in that lattice. And that might be somewhere between 1 and 20 milliseconds.
So T is the tunnel plus turn.
Yeah, so one thing you'll see, and especially in my talk tomorrow, is AMO people are not careful about, they don't always choose the same thing for tunneling matrix element. Some people take T, some people take J, some years take J, other years take T. Okay, so I'll use those somewhat interchangeably. My own group, we use T. Other groups use J. All right. And that's because no one's really seen, or people have just barely seen super exchange physics, so J was not something that J people didn't worry about for a while, so they chose J for tunneling. Okay. Okay, so that's kind of what this stuff looks like, characteristic scales. Okay, so David talked a lot about thermodynamics. Let me talk a little bit about thermodynamics and give you some examples of how we think about this. Let me just say from the offset, well, okay, let me just go here. So these experiments, the atom gas is very well isolated from the environment. All right, there's not a cryostat, there's just the gas. So there's no bath, and we think of these things to 0th order as closed quantum systems. Okay, it's not exactly true, but to a large extent, it's a very good approximation. So now let me just say also, as far as we can tell though, these gases are self-thermalizing. No one's been able to really see a deviation from that. And why exactly that works out? Well, most people believe in this eigenstate thermalization hypothesis for these trapped gases that applies very well. And so we see things that look very thermal most of the time. So approximately conserved quantities in this system are number of atoms approximately conserved. The energy is approximately conserved. And a lot of times in these experiments, we'll slowly change potentials, attempting to be adiabatic. And in that case, the entropy per particle is conserved. If we have slowly changing potentials, of course, we do work on the atoms and energy is not conserved. So I'll talk a little bit about how this all fits together. All right, so in a static case, no time-dependent potentials, number and energy are conserved. A lot of times we try to do things adiabatically. We slowly change potentials. I'll give you an example. That means entropy per particle is conserved, approximately. So good references for learning about thermodynamics in these gases are a book by Pethick and Smith on ultracold gases. And also, 2 of my students went to the trouble to write up a lot of information about thermodynamics, for example, in the various limits. And those 2 theses you can find on my group's website. Let me just find out what's getting cut off at the bottom so I know. Yeah. All right, so let me give you some examples of thermodynamics in these systems just to tell you how to think about it. One example, which I spent a lot of my life on, are ideal fermions at harmonic trap. So fermions which are not interacting, and I'll tell you how you can prepare such a state. We can do that extremely well in these experiments. So semi-classically, we know how to write down the integral for number, right? It's an integral. Here's the integral for number. Inside that integral, there's a temperature, which is associated with the fact that energy is conserved, and there's a chemical potential, which is associated with the fact that number is conserved. Okay, so this integral is what determines, for example, the chemical potential if you know the temperature, because you measured it, and I'll talk about that in a bit here, and it determines things like the Fermi energy. All right, so you can solve this integral. And in fact, for harmonic traps, which is mostly what we work with, these thermodynamic integrals can all be expressed as hypergeometric functions, which are called polylogarithms in Mathematica. Okay, so the Fermi energy in these trapped gases for an ideal gas is h bar omega 6n to the 1/3. That's what you find out when you solve this integral for what happens at 0 temperature. That just means you have 1 particle per state up to the Fermi energy at 0 temperature, and a Fermi-Dirac distribution. I may try to shift things around here to fix this, but here's the occupation versus energy. There's some Fermi energy right here, which is kBTF. And of course, as I increase the temperature, things smear out by kBT around the Fermi energy. Okay, so this is what you're used to. This is kind of textbook physics, and this is really how these systems work. Okay, well, what if we do something a little bit more complicated and ask, how do we do thermometry, which is what your question came to? Well, ideal Fermi gas, we know the solution. So we can do various things. So for an example, we can measure the momentum distribution, which is what I told you about. This is a solved problem. We can snap the trap off. We can let the gas expand.